It is my enormous pleasure, big honor, to begin opening this event, which is called officially Computational Logic, and the conference dedicated to Melvin accepted birthday. And it will be probably a split opening, so we'll open tomorrow today, and we'll have a joint session of the Computer Science Colloquium, which is a normal slot for it, and the conference. And then we'll have the whole day tomorrow with a couple of small speeches probably at the beginning as well. My pleasure to invite the King, Professor King, who represents both Lehman, the place where Mel was hired officially, his wife, I guess, and the Credit Center, where Lehman is now the law, mathematics, and computing program mathematics.
So, on behalf of the math program at the Graduate Center, I want to welcome you all to this conference. It's really a delight to be able to honor Mel. And when I was trying to think of how to make nice remarks about Mel, I thought, well, you know, he is so much better at finding the bon mot and the right thing to say and the right pun that I've just got to play this straight. Mel has been my colleague for more years than either he or I would like to admit. We started both at Lehman about the time Lehman started, so we've come up through the ranks together, and we've worked together in the department at Lehman, also here at the Graduate Center, where Mel has had 3 feet, one in math, one in computer science, and one in philosophy. And he has always been a marvelous colleague. He's a good friend. He's interesting. He's funny. And I'm really pleased to be able to say these few words to you in his honor. So, Mel, congratulations, and I hope you have a wonderful conference.
Thank you very much. Well, 3 feet. The second or whatever, ordered, let me say, because which feet is more cheerful. Okay, Ted Brown, the EO of Computer Science program.
All right, thank you, Sergey. Welcome everybody on behalf of Computer Science at the Graduate Center. I've also known Mel for a number of years. I was trying to think of something fitting.
That's very Melish.
I know, I have a few more. He's been in our department. He's a member of 3 PhD programs, and our department, I claim him as ours. He's really been a mainstay, a pillar, or even, you might say, a cornerstone of our department. For many years, he's taught our first-year course in Logic of Computer Science, and done a wonderful job of teaching and jokes, and we're really going to miss him. He's just such a cornerstone of the department. He used to, when he first started, he was 6 feet tall. He's been holding up the department.
It's true, this place wears you down.
So what I thought, rather than talk about his scientific achievements, which will happen in the rest of today and tomorrow, I thought I would butcher a poem that he's written, and it's on his website. You can read this as you will. I'll read it as I will. We'll try and do justice to this. So he's on his website. He has stories and poems in a separate folder. So we'll pass the worthy worthies on the road in our plodding, nodding way, but we'll gather all the halos with chutzpah, hosanna, and hurry, just because they are they, and hell to pay won't ease the load. But sunlight glimmers in the morning on my tea. and I will see what is prime, what is major, most sublime, what is best to be is not bloody nor too bowed. We'll miss you.
And from philosophy program, the distinguished Professor Graham Priest.
Okay. 2 minutes ago, Sergey told me that I'm representing philosophy, which is kind of interesting. All right, I've only been at the Graduate Centre a couple of years, but of course I've known Mel's work a lot longer, and I always read it with pleasure and joy, because Mel is not only an outstanding logician, and there are a number of outstanding logicians in the room, but Mel has a gift of not shared by all logicians, in fact shared by very few logicians, in the way that he writes. It's always beautiful, it's elegant, it's a pleasure to read. So you not only sort of learn the mathematics when you read Mel's work, but it's just a beautiful piece of writing. And there are not many logicians of whom one can actually say that, so I'm delighted to be able to say that about Mel. And I think I've said enough.
And now, Melvin.
Thank you very much. It's a real pleasure to be here. I'm sorry the talk was delayed because of the problems with the computer, but they are fixed now. And in fact, this is my only slide. Now, what I wanted to talk about, there are several things I've done over the course of a very long career. And I thought rather than talk about what I'm currently working on, I would go back and talk about some work that I did some years ago, which others have continued. This is work on bilattices. Bilattices have applications in several areas, and in both computer science and in philosophy, which I'll talk about briefly today. So I want to begin with Kripke's theory of truth. I'm rather happy that Saul isn't here because he would explain what I was doing wrong with it. Kripke's theory of truth is meant to address the following problem. If you have a language in which self-reference is possible, so you can say this sentence is true or this very sentence is not true, what do you do with truth values? And okay, the usual ad hoc solution is, well, sentences like that don't have truth values. But the problem is not to say this one doesn't, but which ones do. And that's what the theory was meant to address. It introduced a truth revision operator and looked for fixed points in that revision operator. So here's a very simple setup to show the idea of the truth revision thing. So it's a little hard to read from this distance. So suppose you have a bunch of sentences. Sentence A says today is October 4. Sentence B says sentence A is true. Sentence C says sentence B is false. And sentence D says sentence C is false and sentence A is true. You want to assign those coherent set of truth values. In this case, there's no self-reference, so things are relatively straightforward. You start off by assigning each of them unknown. Then you start revising. Now, first of all, this one can be assigned true because it's an outside fact. On the next revision, since A has been assigned true, sentence B can be assigned true. On the next revision, since B is assigned true, C gets assigned false. On the next revision, because of the combination, the way it works out, sentence D gets assigned true, and after that, nothing changes, so you've reached a fixed point. What you need to show is, well, how is this truth revision operator defined, and why does it reach a fixed point? Of course, one of the things that makes Kripke's theory interesting is there's not just one fixed point, but many, and what you want to do is look at the structure of all of them. It's no good if there aren't any, so you need to show there's one. Now, the problems come in with things like this. Sentence A says sentence A is true, which could have, if it's true, it will reevaluate to true. If you assign it false, it will reevaluate to false. So there's no good reason for assigning it one or the other. B, which says sentence B is false. If you assign it true on revision, it becomes false. Then on revision, it becomes true. So it simply doesn't settle down. So in a sense, so A is compatible with anything, B is compatible with nothing, but the things we're talking about here are classical truth values. So what Kripke did was use a three-value logic, where your values were true, false, and undefined. And he defined a truth revision operator in that setting. He showed it had fixed points. As a matter of fact, and these fixed points then become natural candidates for assigning truth values. Now, as a matter of fact, there are several different three-valued logics. Kripke worked with three different ones. What's called the Planey weak, the Planey strong, and supervaluations. I'm going to concentrate on the Planey strong here, but the other two fit into the context of what I'm going to be talking about as well. Time is limited here. But all of these have a certain common problem. Given where we are and who you are, you're probably familiar with the Knaster-Tarski theorem, which says monotone operators on a complete lattice have a fixed point, smallest fixed point, also a largest, and so on. The problem is that with three truth values, you're not talking a complete lattice anymore. It's a different structure. Now, there's a way around that. There are generalizations of the Knaster-Tarski theorem that apply to structures like that. And here's a reference working out the mathematics and applying it directly to what Kripke was doing. But some time ago, Newell Belknap, or maybe Mike Dunn, I'm not actually sure who actually invented the four-value one.
I'd say I did.
Okay.
And if you look at his first two papers, you'll find the reference.
Okay, thank you. So this is Belknap's Dunn's logic. It's a four-value logic. And it was later on, Matt Ginsberg introduced what became called bilattices. And this is really the simplest example of a bilattice. And what I realized at some point is that the entire of Kripke's theory worked very well, not just on that bilattice, but on any bilattice meeting certain minimum conditions. And you'll see what they are in a minute. They're really pretty minimal. So moving to bilattices adds a level of abstraction that generalizes the thing to settings that are interesting and simplifies the math. Now, so what I want to do is discuss bilattices. Now, so a bilattice is a set with two different lattice orderings. The lattice orderings have to be connected, or otherwise you really have two different subjects you're talking about. Sorry if I keep hitting this. I'm not mad at it. I'll assume the lattices are complete for this talk. That completeness essentially lets you interpret quantifiers, but we don't need to go into the details here. So the question is, how are they interconnected? Well, all right, so first the basic machinery. Let's call a pre-bilattice a set that's B with two orderings on it. One of them is ordering called T, less than or equal to T. That's a truth order. So in that ordering, as you go up, the degree of truth should go up, or the degree of falsity should go down, or something like that. We'll see something more concrete in a minute. The other one, the K ordering, it's K for historical reasons, but it's really an information order. As you go up in that, the amount of information you have goes up. Now, information can come from a variety of sources. You might know more, or people might have told you more things, and the things they told you could be in conflict. So you've got more information. It may not be particularly helpful, but you've got more information. All right, so both of these orderings should be lattice orderings, bottom, top, so on complete lattices in both directions. And Matt Ginsberg introduced these in an AI setting in the 80s. His connection between the two orderings was through negation. That's an interesting connection, but it turns out not to be what we really need here. We need something stronger. So, okay, first of all, some lattice operations here. I need to just introduce some notation. For the truth ordering, this T ordering, meet, join, greatest lower bound, least upper bound. I'll use the and or notation from logic. Similarly for infinite, the smallest element I'll call false, the biggest element I'll call true. For the knowledge ordering, I'll use O times and O plus for the meet and join. The smallest element, I'll just write bottom, no information. The biggest element, I'll write top, way too much information. This operation, it's sometimes called consensus. It's what different sources can agree on. And this is gullibility, belief at all. It's an election. All right, so I'm assuming these 4 extreme values are all different. So it doesn't collapse in any trivial way. So here's this 4-value bilattice, which here says Belknap and should say done.
Small correction, put me on the spot there. With great deference to my teacher, I did make the true claim though that the 4-valued logic, that is that 4-element lattice, was due to me. But I would add quickly that he's the one who saw it as a bilattice. I never did that.
Okay. All right. So here I'm representing the truth ordering in the left to right direction. So false, the smallest, is at the extreme left. True, the biggest, is at the extreme right. The information ordering, bottom up, no information on the bottom, too much on the top. And here are the conditions connecting them. There are 2 different ones you can consider interlaced. So all the operations are monotone with respect to both orderings. It's hard to see. So it doesn't matter that I wrote this. It doesn't mean I remember it. So what the example here says is if A is less than B in the truth ordering, then A join C is less than B join C in the truth ordering, but the join that you're seeing here is the one of the information ordering. So it's going across orderings. So the interlaced conditions are all operators are monotone with respect to both orderings. The other condition of interest is being distributed. So all distributed laws hold. Here's an example. You notice the and here is the join of the truth ordering. The O plus is the meet of the knowledge ordering. You want the one to be distributive over the other. You want all distributive laws to hold across the 2 orderings. Being a distributive bilattice implies being an interlaced bilattice. That's very easy to show. And Belknap's example is in fact distributive. It turns out there are lots of distributive bilattices. There are bilattices that are interlaced but not distributive. So these are real distinctions. All right, I want to introduce a few more operations: negation, conflation. Negation operation should just turn the truth ordering around. So it should be an involution, and it should leave the knowledge ordering, the information ordering alone. I'm not saying all bilattices have such a thing, but certainly the Belknap one. Let's just flip it this way. The conflation operation is the same thing in the information direction. It should switch the bottom and top around and leave the truth ordering alone. What we want is if a bilattice has both of these, the 2 should commute with each other. And again, the Belknap lattice is an example where all of this happens. All right. Now, so you've seen one example of a bilattice. Where do bilattices come from in general? Well, let me show you some very natural examples. Well, first, a fairly obvious one, the function space. If you have a pre-bilattice and a set, look at all the functions from the set to the bilattice. Give them truth and information orderings by ordering them pointwise. Function f is less than function g in this ordering. If function f at each value is less than function g at that value. Well, that gives you a pre-bilattice structure on the function space. It will be interlaced if the underlying bilattice is. It will be distributed if the underlying bilattice is. So, okay, that's fairly straightforward. Also, if you have a negation and a conflation, that's inherited by the function space. But here's something a little more interesting. Suppose you have a set of people with opinions. A little far-fetched, but suppose you do. So on a particular question, let Y here be the set of people who will say yes to that question, and let N be the set of people who say no. So that gives you a pair, the yeses and the nos, and think of that as a generalized truth value. Now, you don't have to assume that everybody has an opinion, so the union of the two might not be all the people. You don't have to assume that people are internally consistent, so somebody might say both yes and no. Okay. And we need to define an information ordering and a truth ordering. The information ordering, one of these pairs is below the other if the collection of people who said yes goes up and the collection of people who said no goes up. That gives you a lattice ordering. And for it, the meet and join is just meet is intersect both components, join is union both components. No information is nobody said yes, nobody said no. Too much information is everybody said yes, everybody said no. For the truth ordering, let's say one yes-no pair is below another yes-no pair. If the set of people who said yes went up and the set of people who said no went down. So notice the second thing has been reversed there. The N2 is subset of N. So truth goes up if the yeses go up and the nos go down. This also gives you a lattice ordering. For this one, your meet is intersection of the yeses, join of the union of the nos, and similarly the other way around. False is nobody said yes, everybody said no. True is everybody said yes, nobody said no. There's a natural negation. For the negation, just switch around the yeses and nos. There's a natural conflation. This is a switch around and complement, but what it amounts to is think of the yeses as the people who weren't nos. And think of the nos as the people who weren't yeses. So this is a conflation operation. If you only have one agent, this gives you Bell-Maps logic again. But there's nothing there. Okay, so what I didn't say here was this, in fact, always gives you a distributed bilattice with a negation and a conflation. So there are lots of examples, and in this family, Bell-Maps is one of them. All right, so this can be generalized further. You could have different sets of people voting for and against, not necessarily the same people on both sides. If you do that, you can get an interlaced bilattice without it being distributed. But this is far enough for now. Here's another example. Take as the bilattice members ordered pair where they are numbers in the interval 0, 1. So think of the first thing as the degree to which you believe something, and the second is the degree to which you doubt. It's very similar to the other example. It's a kind of a fuzzy truth example. Again, the information ordering, the degree of belief goes up, the degree of doubt goes up. The truth ordering, belief goes up, doubt goes down. Should sound familiar from the other. This becomes your meet and join. This becomes your negation and conflation. Again, this gives you a distributed bilattice. This can be combined with the other. You can have sets of people who have fuzzy opinions. But these are in fact special cases of a general construction. Take two complete lattices. Define a pre-bilattice by, Cartesian product, that's your carrier set. Define the truth order, this is the information ordering. One pair is less than another pair. If things go up in the first component using the ordering of the first lattice, they go up in the second component using the ordering of the second lattice. define a truth ordering. Things go up in the truth ordering if they go up in the first component in the first lattice and go down in the second component in the second lattice. That's exactly what was happening in the cases you saw. This is always an interlaced bilattice. It's distributive if the two lattices involved are distributive. If the two lattices are the same, then this operation will give you a negation. If the two lattices are not only the same, but you have an order reversing isomorphism, then you can define a conflation, switch things around, and reverse it in the lattice. Negation and conflation will commute under those circumstances. Not only that, but this is a completely general construction. So every interlaced bilattice is isomorphic to a product of this sort for lattices. Every distributive bilattice is isomorphic to a construction like this, where you have distributive bilattices you're putting together. Every bilattice with negation is isomorphic to lattice times itself for some lattice. Every bilattice with commuting, negation, and conflation is isomorphic to something like this for some lattice with an involution. This is a complete representation. There are other bilattice constructions as well, but this one gets you all of them. All right, now, how does this relate to what Kripke was doing? So he just had true, false, and undefined. In a bilattice, call something exact if it's its own conflation. So in effect, reversing the amount of information doesn't change it. Call something consistent if it's below its conflation. This is in the information direction. In the Belknap bilattice, the things that are exact are true, false, the classical values. The things that are consistent are the values of the claiming doctrine. The thing is, if you work with any bilattice, the things that are exact are a natural generalization of classical logic. The things that are consistent are a natural generalization of the claiming doctrine. Now, I don't have time here to go into what natural means, nor do I have to go into what generalization means. So the question now is how do fixed points come into it? So remember you have this truth revision operator that Kripke had. Well, okay, we want to use the Knaster-Tarski theorem. So that says a monotone map on a lattice always has the smallest and the biggest fixed point. So it's a well-known standard theorem. All right, so suppose you've got a map from a bilattice to itself. And first of all, suppose it happens to be monotone in both of them. You'll see an example later on. Then it has a smallest and a biggest fixed point with respect to the information ordering. And I'm using little s and big S for smallest and biggest, sub k for the information ordering. Similarly, it'll have smallest and biggest fixed points with respect to the truth ordering using ST. Okay, so this is not only a fact, but an obvious fact, that they're related, those four fixed points are related this way. Why is that obvious? Well, this is the biggest fixed point in the information direction. These are fixed points, so they have to be below this. And the same kind of argument works all the way. But there's much more to the structure than just they're related. You know, this is below this, to the left of this, and so on. If the bilattice is interlaced, the smallest fixed point in the information direction is the information join of the two extreme fixed points in the truth direction, and so on all the way around. That is, from any pair of these, you can calculate the rest. Which is a very nice, coherent structure here. Now, theory of truth. Okay, so the language background, just very quickly. Formally, you have to bring something like arithmetic into it, but let's just assume you have a language with in which self-reference is possible. Say Gödel numbering is available. We don't have time to go into the details. And in fact, if you number Gödel, it's just one. But think about that. So let's assume we have a language that extends the language of arithmetic. So for a formula, I'll assume this with the angle brackets is a numeral we can think of as a name for the formula. There's a one-place predicate symbol, T, that's meant to represent an is true predicate. Truth predicate. There could be other predicates too, like is a cow or is a pillar or something like that. So we have intended models. We're assuming they all have the same domain, and among them is numbers, but there could be cows and pillars too. The interpretations are standard on arithmetic expressions. So arithmetic behaves the way arithmetic is supposed to behave. Non-arithmetic and expressions are interpreted the same way at all intended models. So if something is a cow in one model, it is in all the models. So the outside world is sort of fixed. What we're interested in is how do we interpret this truth predicate. Okay, so evaluation, now since that's the only thing that's up for grabs, evaluation is a mapping from closed formulas of the form something is true to, let's say, the Belknap binomials. So we're assigning a truth value set, or to any distributed binomials. The details aren't going to matter. And this just says what to do if you're applying t to something that isn't a natural number. Just take it to the bottom. The space of valuations is itself a bilattice. We saw that before. The function space would be itself a bilattice. Extend evaluation to assign truth values to all sentences, not just sentences that say something is true. If you've got a relation symbol other than true, in effect, it behaves the same way in all the models. Call it true or false, depending on your intended interpretation of these things. So that's a pillar in all models, so that is a pillar is true in all models. And build up how you calculate truth values of more complicated formulas in the obvious way. I just told you what to do with the atomic case. But how do we take ands and ors? We're using the meet and join of the truth order. That applies even if something was assigned bottom as its truth value or top as its truth value. This makes sense. And so notice for figuring out truth values of sentences, we're using the truth order. And this just says how to handle quantifiers. They're handled like in infinite ands. Now, we want to produce evaluation giving this truth predicate a meaning that comes as close as we can to what we think of as the intuitive meaning. And a minimum requirement is the value you assign to x is true should be the same as the value you assign to x itself. Now, and that says you're looking for a fixed point. Now, the trouble is you have these self-referential sentences, truth tellers and liars, and this is the problem that all of this was designed to address. So I'm just using this notation to indicate that x and y have come out to the same value. It's not something that's expressible in the language itself. Now, for a truth teller sentence, it should have the same value as it is true. Any value will do for that. We saw that before. For a liar sentence, well, it's not the case now that there are no values you can assign to it. Bottom and top will do in the Belknap lattice. In other lattices, other things might be there that won't work. Classical truth values won't work. So, we talked initially about a truth revision operator. So we want an operator that maps valuations to valuations. Well, if you have a valuation v, give that as input. You can't see where I'm pointing, I know that, but it's psychological on my part. So you assign this value v to the, you give up this value v to the operator phi. What you get out is a valuation. Well, it's the valuation that assigns to the sentence x is true, whatever the input valuation assigned to x. So you start with a valuation v, you compute phi of v, which is now a new valuation. What you want is a fixed point of that. We use the truth ordering to get how we figured out truth values of our sentences. But what we're going to look for is a least fixed point in the information direction. Well, it's pretty easy to show that, well, it says it's straightforward, so it must be straightforward, that if this valuation is less than that valuation in the information ordering, the value it assigns to each sentence will be less than the value it assigns to each sentence. There are two bilattices going on here. One is the valuation bilattice, and the other is the underlying bilattice. This also works in the truth direction, but only if you don't have negations present. That's going to throw things out. That's why finally you don't work in that direction when you're looking for fixed points. But the fact that this thing on top here, that it works in the information direction, makes use of the interlacing conditions. Remember, and behaves nicely with respect, the truth and behaves nicely with respect to the information ordering and so on. That's exactly where they come in. So what all of that gives you is that this truth revision operator is monotonic in the information order, in the function space evaluations. Since that's a, well, here's a proof, but never mind the proof. Since that's a lattice ordering, Transvitarsky says it has the smallest and the biggest fixed point. Right. So the smallest one, in fact, is the one that Kripke was looking at. It's within this consistent part of the lattice. So these are natural candidates that take is true into account. And this construction, in fact, works with any, it says bilattice here, it should be with any interlaced bilattice. So we can call these Kripke fixed points, and this is almost what Kripke did. He only had the consistent part of the Belknap lattice to work with. And what we're doing is just the Kleene strong three-valued logic. But I said there were others. Any interlaced bilattice will do, as well as the Kleene logic. Let me hold that one a minute. The other two logics that Kripke worked with can also be defined in a bilattice setting. Everything that Kripke was doing carries over to them too. I just don't have any time to discuss that now. So this is really a very broad area of applicability for this. Kripke introduced this notion of intrinsic fixed point. It was also introduced in computer science independently. An intrinsic fixed point for him was one that was compatible with all other fixed points. And he showed there were intrinsic fixed points. So that what it meant for in his setting was if it assigns a classical truth value, every fixed point has to assign the same value. That can be generalized to bilattices. A fixed point of this truth revision operator is intrinsic if the information join of it with any consistent fixed point is another consistent, is consistent. Then the whole of what Kripke was doing with intrinsic fixed points carries over to arbitrary bilattice settings with essentially no change in proof. One of the things he showed was that the least upper bound of the set of all consistent intrinsic fixed points exists. In fact, it's possible to show that if you start this truth revision with, I'm sorry, I said that, I left something out there. If you look at this, yes, the least upper bound under the information ordering of the set of all intrinsic fixed points exists. What in fact happens is if you start the truth revision operator from there and work your way down, you come to essentially the largest intrinsic fixed point. I think I'm saying that wrong. Forget that. Anyway, so this was the Kripkean part. There's a second part, which I will be much shorter about. Oh, I'm sorry. This is the part 1.5. This is just to fill in what I was saying about there being other logics. I forgot it came up here. Point is very simple. All of them work. And I'm not going to have time to go into it. This is the second part. Many of you are in computer science. This whole structure is sort of in the background in the semantics of logic programming as well. Semantics. So in logic programming, a clause, which is going to make up as the basic building block of a program, you have a head provided a body, and here's an example. This H predicate holds provided the P predicates hold and the Q predicates don't, very roughly. So the capital letters are relation symbols, the little letters are sequences of terms, and I don't want to go into the details now, but they are essentially a form of implication. The H provided the other things. If you don't have any negations, that's called a positive clause. And a logic programming is program is a finite set of clauses. It allows variables in terms, but there are also extended programs, disjunctive programs, which I'm not going to get into here. So here are some examples. Suppose you think of the non-negative integers as the symbol 0, successor of 0, double successor of 0, and so on. Then here are characterizations of the even numbers using logic programs. This just says, as a fact, 0 is even, and double successor of x is even, provided x is even. The x here is a variable. This one doesn't involve negation. It's a positive program. Here's another one that does. 0 is even, and single successor of x is even, provided x is. Both of these work very well in logic programming. So this one uses negation. Here's a game playing example. Suppose you have two players, A and B. There are positions, and that depends on which game you're playing. There's a table giving moves for each player. So you've got, there's a move for player A from this position to this position, and so on. Okay, so here's essentially a game playing program. Position is a win for A, provided there's a move for A from position to new position, which is not a win for B. And same the other way around. This works. I mean, you can simply type it in and program it. But you also have these problems. This is a perfectly good logic program, A if A. This is another perfectly good one, A if you don't have A. And you should recognize the analog of the first one to the truth teller in Kripke's theory, and the second to the liar paradox. This one is a little more complicated, A if not B, B if not A. But the thing is, one ought to suspect that something similar will apply here that applied in the Kripke case. And it does. So first let me do the usual cheat here of working with what are called ground logic programs. What you do is simply take all instances and you don't worry about how variables get instantiated. You should instantiate them all up front. It is cheating, but it is convenient. I mean, there's no point in cheating if it's not convenient. So I'm going to assume the programs are ground now. So here is an example. We had this evens thing before, and you've got all the ground instances. So as valuations, you want to assign these little bits that when it made up the logic program, values. Values now are going to be true, false, but they could also be undefined. A provided not A. The A is not going to wind up being true, it's not going to wind up being false. So we could have undefined, we could just as well have overdefined. Which suggests bringing the Belknap lattice back. Or it could be another distributed lattice. Extend valuations, so the valuations here just map atoms to the Belknap lattice. Extend valuations to the clause bodies by thinking of the body as a big conjunction, and evaluate the conjunction using the operation of the truth order. Space evaluations, again, will be another distributed line lattice. Set up an analog of the truth revision operator. So it will map an input value. You have, say, a grounded program key. The truth revision operator will map an input valuation V to an output valuation W, where the value that W assigns to an atom is look at all of the clauses in your program that. Let me start this again. The value that your output valuation assigns to atom A is look at all the clauses in your program that have A in their heads. See what values the input valuation assigns to the bodies, and take the truth OR of those. So again, we're defining this using the truth order. This mapping will map exact valuations to exact ones, consistent ones to consistent ones. If there are no negations, it will be monotone under the truth ordering. And this, in fact, is a standard fixed point semantics for logic programming due to Abt, Van Emden, and Kolomsky. It gives you what's called the least Heron model. But things get more interesting if you do have negations. It's not monotone under the truth ordering. But it's still monotone under the information ordering. So what you want is the least fixed point in the information ordering, and that gives you a semantic called Kripke-Kleene semantics. Why the name? Well, you see the connection with Kripke's use of Kleine's three-valued logic, and it was simply transferred to this set. You could consider it, but we don't really have time. Intrinsic fixed points were invented independently in the computer science community, and I'm not going to do anything with them here, but they were introduced more or less in this context for the same sort of reason they were introduced in the theory of truth context. And results in one area transfer to results in the other area and back. Can one do better with respect to negation? Yes, there's an alternating fixed point construction. One of the problems with P if not P is it keeps switching back and forth. And there are fixed point theorems having to do with what are called alternating fixed points. So instead of a fixed point, you get two things that map to each other. All of that can be done here. I don't have time to discuss it today. It leads to what's called the answer set semantics, which was actually introduced by Gelfand and Lifshitz, one of these here. And in a sense, this is the abstract generalization of that. But I don't have the time today to really go into that. Let's just say it works naturally in a bilattice setting generally. So what it does in the logic programming community, you will hear some of tomorrow. In the theory of truth, what it does is provide a family of Kripkean fixed points that favor false. It's an interesting family that really hasn't been looked at. It's possible to show no member of that family is intrinsic. But it's also possible to show there is an analog of intrinsic relativized to that family, and that hasn't been investigated at all. So there's some work there. Okay, this says what I just said. Redundancy is good. So that's about it. All of this is old work. Since then, bilattices have been applied more generally. I was looking on the internet today to see what people were currently doing. There's fuzzy bilattices. There's bilattices applied to intuitionistic logic somehow. So it's gone off in interesting directions. This work of mine is a number of years ago. It's gone on, but it's an interesting classical thing. What I did was essentially the algebra. Arnon Avron and some of his collaborators worked out what's the logic of all this. That's another whole subject that I'm not going to have time to get into today. It says here that's somebody else's talk. Here are some bibliography references, which I'll go through too fast for you to read. There's the Belknap paper, Kripke's paper on the theory of truth, which is now available in a number of places. Visser, four-valued semantics and the liar, Yablo on truth and reflection. Papers of mine directly on bilattices and theory of truth. Averin and his collaborator one here. And George Gargoff, which was, I should say something about, very scholarly, nice man. And at one point we formed the plan of writing a book on bilattices. And he got as far as writing this and died. And this was found in his computer after he died. It was sort of the prehistory of bilattices. Many of the ideas had been discovered more than once. And he found this out, and it's a nice paper. But the book never got written, and as far as I know, no book has been written. But anyway, that's it. Thank you.
There's some reasonable time for questions. Scientific talk.
That was easy.
No, I'm sure because it's not
You said it all.
Oh, you know I'm present.
I not really said all, but I said more than that.
I recognize the truth and knowledge orderings from the context of natural dualities. Would you like to say anything about that?
No, because it's something I'm not really knowledgeable on. But would you?
Me neither.
Okay.
Yes.
Mel, in your work on semantics and logic programming, at some point you use three values and then you add a fourth. In terms of applications to logic programming, what do we gain from the fourth value? How does it change our view on logic programs?
There were really two reasons for moving to that fourth value. It doesn't come up with ordinary logic programming, but it does, in some sense, simplify the math. It gives you a lattice structure. So it gets you the results you need to justify the background stuff more easily, even if it's not going to come up in practice. But the other thing was, I had in mind a notion of a distributed program where parts of it were running on different machines and then being combined, in which case you could get conflicting information. And this can handle it.
Just a brief question. Clarify situation. If you take the collection of fixed models, minimum fixed models, so this by itself, for every fixed model, it's more than 6 dimensions. What is your logic? How is this?
I don't know. I don't know. I mean, with the Castor Tarski theorem, the collection of fixed points is another lattice. I don't know what the situation is here. It's a good question. I don't know.
Yeah, I might actually comment a little bit on the early history. I mean, I was a student of Newell Belknap's and sort of observed, his interactions. Dana Scott is the one who I think first perhaps saw the idea of the fourth value. He called it an approximation lattice. And there was the truth order and there was the approximation order. And I think that really influenced Newell's seeing, the two orders, right? Which then Ginsburg came along and baptized and promulgated and generalized, so on, right? With these labelings, the knowledge order and the truth order, right?
Yeah.
Belknap talked to the logical order and the
Yes,
I don't
yes.
like inconsistent knowledge, and that's where you
Right.
sort of end up
Right.
with information.
I kept the K here for
Yeah,
historical
it's for
reasons.
historic, I've done that.
Yeah, yeah.
So I just thought I would add Dana's name to
Mhm.
it.
Good, good. Now, one of the things I was thinking of, and the things we're anticipating, this idea of a construction where you have a pair of things, and information goes up if both go up, and truth goes up if the first goes up and the second goes down, was discovered a number of times. That it gave you a full representation of bilattices, I don't think was known because there was no general notion of
No, I
bilattices.
agree with that. Yeah, that representation was actually in my dissertation. But I'm embarrassed to say when that was. 1966. And, but I had no idea at the time. But yeah, I just turned it on the side. You got this other interesting information on it.
Yeah.
But that's where the four value logic originated, actually. With my thinking that proposition surrogate, as I called it, had two parts. The sort of positive content and the negative content represent the Morgan lattices.
Questions? It's nice to give a talk in a room where there are people who are actually experts on parts of these things.
More questions? Maybe I'll ask a very stupid mathematician's question. Trilattices?
Yes, there are. I don't remember who introduced them. I didn't find them natural. I mean, it seemed to be simpler to stick with the bilattice construction and in effect iterate it, so you got 4 orderings and shorts. And then if you want 3, just forget the 4th one. But it seemed to have more mathematical coherency.
I hate to be so much in the middle, but that's my knowledge. Trilattices first appeared in a paper by Franco,
Yes.
Takanaka, and myself.
Okay.
Right. And then Bossing and Franco went on to, do them in all kinds of different ways. In lattices. Quite right.
Yeah.
The famous anecdote about the mathematician Joseph and the general talk about evolution and the theory. And he said, we can generalize it to n sexes. Right, more questions? At this note, we'll probably just thank the speaker again.
Mel really did, talking about evolution, he really transformed the study of our lives. Ginsburg was clever with labeling and so on. Nice paper, but I think Mel really took it and ran with it.
We'll try to arrange a couple of speeches during the dinner, yes? Everybody is invited downstairs. There's enough lounge, there's a small reception here.